So I'm going to start by showing a bunch of pictures. I think talks are more understandable if we give a picture instead of a lot of equations. And you will see a bunch of these pictures throughout the talk. And the reason why I put them together is because some of them are physical. So it's just a lake. This is the Bose-Einstein condensate. And then this is just a representation of forward cascade. And some others are more mathematical, such like this guy here. I will explain what it is, this one, and some Feynman diagrams, and so on. So what I want to do today, though, is to give a little bit of a sense of how much different kind of mathematics has been used in the study of wave turbulence theory. So I'm here representing the Simon collaboration on wave turbulence theory. And I have to say thanks to my co-PIs and the postdocs and grad students I worked with, I learned about a lot of other kind of mathematics than just the harmonic analysis I was trained on at the beginning and the basics of PDE. So I'm not going to read all of them. And of course, I will not be able to give you examples for each one of these subjects throughout the talk, but hopefully I will touch upon some of them. Now, we talk about wave turbulence, and in fact, I went to the webpage of our collaboration, Simon collaboration grant, and that's what we wrote as an explanation for the general audience of what wave turbulence is. So when you have a physical system with a large number of waves interacting, it's not important to understand the evolution of each single wave. What's important is to understand how that interaction produces something that we can see macroscopically, whatever the phenomenon might be. And so what becomes physically important is practical use, our density, and the statistics studies of the interaction of waves. And this is what, for this lecture, will be the meaning of wave turbulence theory. So tonight we will encounter some of the tools that us mathematicians use in order to give a mathematical theory. Of course, there is a very, very rich physics there around the wave turbulence that puts together experimentation, both physical experimentation and numerical experimentation and so on. And then there are the mathematicians that try to put in that solid background what the physicists tell us that happens. So I'm going to just give you more pictures. And the statistical description of this system of interacting waves are important because they show up in many different fields. Of course, we don't study all of them, but I just want to give you at least some ideas. Gravity, internal waves, that's a picture of the ocean, and internal waves are this little dribble here. Today, when we had our meeting with the co-PIs, we talked a lot about that. And I already mentioned the Bose-Einstein condensate. So the rigorous derivation of this description in different settings, because of course depends what scale we're looking at, what are the parameters that are involved and so on, are really fundamental problems in mathematics. So let me start with something that it's not wave turbulence, but it's some phenomenon that maybe people are more familiar with. So what you see in this first picture here is a box with a gas, and the blue dots are supposed to represent particles. It is very important in physics and also mathematics, obviously, to go from the very small scale, the macroscopic, to the very large ones, like I say, what we see really from the interaction of the particles. So the particles interact by using fundamental law of physics. And in particular, when we are looking at gas at this temperature, for example, we will use the physics of billiard balls bouncing against each other, and then there are very geometric pictures that you can deduce here. And then there are limits that are taken. And these limits, I'm not going to say much in details, but these limits are taken depending on what is the ratio between how large the radius of the ball and how the number of the balls are considering. And there is some probability coming in, and there it goes. there is an equation that pops out from this very detailed study where a lot of mathematics in, and we get the Boltzmann equation. So the Boltzmann equation, it's an evolution equation, depends on time, and it tells us and is used in order to determine changes of the macroscopic quantities such as the energy, the particle density, and a lot of other things. So in this story of the gas, the Boltzmann equation is called the kinetic equation of this system. And when I say that here there is a lot of math, there is a lot of math, starting with Lanford and recent work of some of my co-PI, Laure Saint-Ramon and Isabelle Gallagher and Texier. By the way, I'm not obviously, I'm going to cover quite a lot of ground here, so I'm not going to be very precise on who did what, and I apologize for that. I will mention just few people, either because they are like fundamental or because they are a co-PI in our group. So I will take the liberty to do that. So towards the end, I will mention more people because I will emphasize more what we are doing in our group. Okay. So that was interaction of particles, but this talk is about interaction of waves. So let me give you at least an example in which instead of working with particles, we work with little wave packets. So the example that I like to give is this little cartoon here that represents how we get the Bose-Einstein condensate. So what we start with is, again, a box with particles. Now, the difference with respect to what happens for the derivation of Boltzmann equation is that we are going to let the temperature go to the absolute zero. So we are lowering the temperature. That's what's going to happen here. So in those situations, we are not going to represent the interaction of particles like a billiard balls, but instead we're going to represent the phenomena at a very small scale as interaction of little wave packets. Now, if the distance between the wave packets and the little wavelength are not comparable, this is the picture that happens here, well, not much is going on. But as we lower the temperature, then in the next step, we're going to reach a certain critical temperature in which now the distance between the wave packet and the wavelength becomes comparable. And then some interesting physical phenomena happen until T0 absolute zero. You see here the giant matter wave. This is the Bose-Einstein condensate. And this is the kind of situation that we want to study and which is connected with what I wrote here, the Schrödinger equation. So this is the cartoon. And of course, we're going to see mathematically how we can translate the cartoon into something that is mathematically rigorous. So first of all, the small wave packets interacting is the many-body system, and we're going to represent that with the so-called BBGKY hierarchy. The BBGKY are initial of scientists, and I don't remember the name now. And then what we do is take a limit as t go to zero. But it's not as simple as that. Again, there are parameters that you wanted to consider. It depends in which way you take a limit. I'm not going to describe that part. But at some point, by taking the limit, you get the Gross-Pitaviersky hierarchy. Now, I'm not going to I decide not to write the Gross-Pitaviersky hierarchy because, like my friend Tatiana likes to say, this is something that you don't show in public. You see more in the quiet of your room because there's a lot of parameters that are not important for this talk. But the point is that, that I want to make is that this taking the limit in the rigorous way is a very difficult process. And in fact, this has been settled, at least in 3 dimensions, only with a series of papers by Erdős, Schlein, and Yao around 2007. So it's a pretty recent result. And in this hierarchy, this is an infinite hierarchy. So, I mean, there are a bunch of equations. They're all linear, but they are coupled with each other. Inside it, if you like, there is one of the most important fundamental equations in physics, which is the Schrödinger equation, down below here. Okay, so this is going to be sort of the protagonist of what I'm going to say later in the talk. So I would like to at least parse what this is. This is supposed to be a general talk, so let me tell you what each of these quantity are. So I is the complex number. The U is the unknown and is a function in time and space variable. And in the first part, we are taking the partial derivative with respect to time. Here, we are taking second partial derivative in all the directions. And this that you see on the left-hand side is the linear part of the equation. And we're going to learn a lot about that, and I'm going to calculate things with it. But our work is really trying to understand what happens here in the nonlinear part. So this is the cubic nonlinearity. It's the magnitude of u squared times u. And there is a lambda here. It's a constant. And depending on what is that we want to learn about this equation and its solutions, that constant could be positive, negative, or can tend to 0 when we are talking about weak nonlinear settings. And if lambda is positive, it's called defocusing case. If it's negative, it's focusing, and I'm going to tell you a little bit more about that. Okay, so that's a little bit just how one of the most important equations comes in. But this is not the equivalent as the Boltzmann equation. This is a different equation. This is an equation for the wave u. We will be introducing what we call kinetic wave equation, which is in fact describing the energy density of this wave u in a little bit. But for now, we'll study this equation here. Okay, so I just mentioned that what we would like to study is this kinetic wave equation, which is the evolution equation of the energy density. And I just want to say that it's quite remarkable that for the Gross-Petaviesky hierarchy, this infinite series of the equation, there is an equivalent of the kinetic wave equation. It's called, in fact, quantum Boltzmann. And in it, you see both parts of this kinetic wave, but also parts of the Boltzmann. So you see both of it. And we are not going to study this, but we will concentrate on that. Okay, so let's now try to explain what are the difficulties in studying what we call the Cauchy problem of the Schrödinger equation. So a Cauchy problem means that I'm giving you an equation, I'm telling you how the solution u that I'm looking for looks like at time 0. So I'm giving you the initial data, the initial condition u0. This is just a profile. And what I at least want to know is whether if I'm giving you a profile which has the regularity of the two conservation law for this system. This is a physical system, has conservation law. I'm going to describe in a second what this conservation law. This is the energy and the mass. But given an initial profile that has this regularity, do I have a solution? And I will spend a few slides in talking about the fact that this is not trivial, because the regime in which I'm putting myself is not too smooth. In fact, the energy is composed by the kinetic energy, which is the gradient in L2, and the potential energy, which is the L4, with again the lambda, which is the constant in front of the nonlinearity appearing here, and the mass is the L2 norm. And as you can see here, if lambda is negative, there is a competition between kinetic and potential, and that competition might result in blow up, but that's not what I will explain tonight. Okay, so if you want to stay within this regime of regularity, it's not trivial at all to prove that this Cauchy problem is well posed, meaning that there is a solution, the solution is unique, there is stability with initial data, and so on and so forth. So, as I said in this picture, the question now is, I'm giving you the initial profile u0. Do I get an evolution? And here I just represent quickly the solution ut. That satisfies my Cauchy problem here. Okay, let's start. That's too hard. It's non-linear. So let's start easy, and let's start with the linear part. The linear part, this is great news. If you put yourself in the appropriate setting, can be solved completely. We have an explicit solution for it. And in fact, the explicit solution is obtained by using a method of Fourier that he introduced in order to study the heat propagation on an iron bar, for example. So my setting at the moment, an easy setting, is to assume that my initial profiles are going to be periodic functions. And I'm putting myself in one dimension first. Later on, I'm going to tell you how I can go to higher dimension. But let's start easy. So periodic means that either I'm going to look at ux, where x is an angle that will rotate from 0 to 2 pi down here, or you can also represent as its graph that gets repeated. So from whatever happened from 0 to pi is going to happen also from 2 pi to 4 pi and so on. That's what it means to be periodic. If we put ourselves in this setting, then we can do something explicitly. And let me first start with a signal which is extremely simple. It's just a combination of sine and cosine. So if we use this notation, notation, e to the ix equals cosine x plus I sine x, and here is the representation of sine and cosine, then let's think in the simple possible terms, and my initial data is only a constant a times cosine x plus I sine x. So this, you can see it, it's just this very simple waves. Now, I expect that the solution for my linear problem takes the following shape. So I'm expecting that v of tx, solution of my Cauchy problem, linear now, is a e to the ixk, but then there is the action of the equation, and that action I expect to add this modulation e to the it omega. Now, what's omega? Well, like what we tell to our students in calculus, say, well, to see that this is a solution, just plug in. And that's what we do. We plug it in, and we realize after we plugged in, we take our derivatives, that in order for this v to be solution of my Cauchy problem, the omega has to be k squared. And that's the action of the Schrödinger operator. Okay. Now, this is all good, but what happens if my initial data is not as simple as this, right? Not simple like a combination of sine and cosine. Well, the rescue comes from the Fourier Transform. So I like this picture here because this is the most visual representation of what the Fourier Transform does. So we have a signal here, the white light hits the prism, and it gets split into simple parts. So each color here that of the wave that comes out represents a certain frequency and so on. And this is a little bit more mathematical looking type of thing. But basically what the Fourier transform does is the following. I'm giving you f of x, which is a periodic signal. And I can write it, and of course you have to be very careful of what we mean with equal here. So that's why I put equal with a little tilde on the top, because what you see on the right-hand side is an infinite series. So you can write it as a sum of these fundamental waves, e to the ikx, with a coefficient ak here. This is kind of like if you you are in finite dimension, you have a basis of vectors. You can write any other vector as a linear combination of that basis. So here we have an infinite basis that is e to the ikx, where k ranges in the integers, but the concept is the same. Okay, so we also know what these coordinates are. And these coordinates, ak, are called Fourier coefficients, and they are just this integral. You take your original signal f of x, you hit with one of the base vectors, you integrate, it's kind of a dot product for those people that know this stuff, and you get the coefficient. So this is all great because now we are looking at a linear problem, and we can write the initial profile as a linear combination of things. So it's not a surprise that then, if I start with my periodic initial profile u0x, and I write it in my development with my series, oops, I'm sorry. I don't want to show you what comes next, but okay, and I write it as the series with my Fourier coefficient here. Then it's not a surprise that the solution of my problem, which now here, from now on, I'm going to indicate as S of t applied to u0. S of t stands for the Schrödinger group, if you like. This is going to be exactly the sum of what we have found before, except that before we were fixing k, now we're summing over the k, with again, what you see here is t to the k squared. Okay, this is completely explicit, and it's one dimension. Now I wanted to go a little bit higher, and I'm going to warn you that I'm going to stop at 2 dimensions, because that's enough for me to do interesting things, and I don't want to go further because it gets too complicated. So now if we are in 2 dimensions, and we are periodic in 2 dimensions, then we are x, the physical coordinate, is made of 2 coordinates, x1 and x2. Each one of them is periodic, so I'm thinking of it on the circle. But then I can identify these 2 circles, one for each dimension, with this rectangle, where here, for example, in this direction, I'm going to put the purple circle down below in the x direction, if you like. I'm going to put the green circle. And I can identify the 2 sides, the 2 purple sides, and the 2 green sides, and I'm going to get a torus. So from now on, you might hear me saying that I'm looking at the Schrödinger equation of donut. And that just means that I'm looking at solutions that are periodic. Note also that here, in this representation, I'm considering the same period in both directions. So in the x-coordinate, it's 2 pi. In the y-coordinate, it's 2 pi. But of course, it might happen that your function has different periods and different coordinates, and this will change things around. But I will get to that later. And the same, doing exactly what we did for 1 dimension, gives us this formula again. This is again the solution of the linear problem with the initial data, the initial profile U0. It's again a sum, but now the sum is on vectors k, which are 2 coordinates. So this is in Z2. This is the lattice that I just draw over here. These are just made, this is just the positive side, but imagine being on the whole plane. This is just made of points that have integer coordinates. This is the Fourier coefficient, the U0 k. And this is, again, what the Schrödinger operator does. It modulates by e to the I. Oh, sorry, there's no t here. There's another typo. Forget this t. The t only appears near k squared. All right, so we have an explicit solution for that. And now we go back to our harder problem, which is, in fact, really the reason why a lot of theory in harmonic analysis was born. So now I forget for the moment the coefficient lambda. That's not important for what I'm going to say next. I'm going to go back to that later. But now we have this nonlinear part here that we have to deal with. And we're going to transform the Cauchy problem into an integral equation. And this is done via the Duhamel method. This is something not just for PDE, also for ODE. You probably have encountered this. And what this tells us is that the solution U will satisfy this integral equation. It tells you that U is equal the linear evolution that we understand very well right here. And then there is this non-homogeneous term that deals with the nonlinearity and tells you that you have to apply this group again, but now to the nonlinearity, and integrate in T prime. Of course, this doesn't solve the problem because I'm telling you that U is written in terms of U. But on the other hand, it tells you that the setup is such that maybe an iteration method can be applied, and that's what we're going to do. So this iterative method is what we're going to do next. And so what's the obvious, most naive things that you're going to do? Well, you want to find an iterative procedure that will give you a sequence UN. And here we are. So I have the sequence UN. And then you want to take a limit in whatever, of course, you need some kind of topology to take this limit. I'm not going to go into that in details, but really the choice of the topology in which you can actually take this limit is the hard part of this problem. So you wanted to find a sequence, and then you want to find the limit, and then you want to say that the limit is actually the solution. So how do you find this sequence? Well, by iteration. So the first element of our sequence is the linear evolution, which we understand very well. What's the second element? Well, we use the Duhamel formula here. So we leave the first, the linear evolution, and then we have this non-homogeneous term in which we replace the U here with the previous one, with U1. And so that's why you see this tree function, because I'm developing the size of U squared into U1 times U bar 1 times U1. And then you move on, and at position n, you have again the linear evolution, and then you plug in the previous one, UN minus 1 square UN minus 1. And then you want to find the limit. Okay, this is a trivial procedure. And like I said, the hard part is to make sense of this limit. So this is where you have to control products of linear solution. In fact, if you go back here, already in the first step, you see that. You have the product of three linear solutions. This is the nonlinear interaction, and you need to understand how that works. All right, so there are two methods that I wanted to just briefly introduce. One is a completely deterministic method, and this is what gives us the so-called periodic Strickard's estimates. And then the other method, it's more probabilistic. So if we stick to the periodic Strickard's estimates, so totally deterministic, the type of statements that we will make from that is of the following. For all initial profile in a certain set, we obtain blah, blah, blah. If instead we move to a more probabilistic approach, which is based on large deviation type estimates, complicated ones, then the type of result that we're going to get at the end is of the flavor for almost all initial data with the appropriate probability space, we get blah, blah, blah. Okay, so I'm going to first stick to this totally deterministic one, which is the one where I have been working more. And I wanted to make some remarks. So these Strickard's estimates actually were people in around 1990 or so were thinking about obviously trying to prove them, and they were already proved in the situation which was not periodic. So when you are in all Rn, the Strickard's estimate were obtained thanks to theorems in harmonic analysis that go under the bigger umbrella of Fourier restriction theorems. But now here we are now looking where instead of, so the solution actually looks quite similar, except that this sum is an integral. And when you have an integral with an oscillation here, what you do is a bunch of integration by parts, and you get decays and you move on and you're good. But if you have sums, that's not possible. You cannot integrate by parts. And in fact, these oscillatory sums live in the area of analytic number theory. So Bourgain in 1990 was asked to, well, the story is a little bit longer than that, but in any case, he came across this problem, let's put it that way, and he started working on it. And in fact, his goal was to estimate the product of four linear solutions the way I wrote before. And it turned out that in doing that estimate, in a spaces, Sobolev spaces based L2, okay? That's where most, the natural space, because we already saw there is the kinetic energy, the mass, they're all based L2. And in doing that estimate, he came across one particular question that is really in the area of analytic number theory. And what he had to do in order to conclude the estimate was to count how many points in the Z2 lattice sit on this circle of radius r, and in terms of r. So you want to estimate that. Now, you can think geometrically, just like the picture I give here. The green dots are exactly what you want to count. Or you can think of it in a number theory way, which means like in how many ways you can write the square of a natural number in terms of sum of squares. Or in other words, how many solutions does this Diophantine equation has? And luckily for Bourgain, and luckily, well, not luckily, but he actually knew about this kind of number theoretical stuff, there is a Gauss lemma that tells you exactly what the estimate is, and this is this one that I wrote, which is less than r to the epsilon. And for the expert of the audience, that means that you lose an epsilon derivative in this estimate. Okay, but this, remember, is the situation in which the torus is square, 2 pi, 2 pi. All right. So, but what about when that's not the case? And in fact, we have different periods in the different coordinates. So let's say T1 and T2. And if the ratio between T1 and T2 is a rational number, what Bourgain used still applies. You still have a Diophantine equation. You can calculate how many solutions and so on. But if T1 over T2 is an irrational number, then you will need, for example, this type of estimates, where here now, just for you, to just understand the idea, I put square root of 2, which is a very rational number. And the estimate of this is actually much harder, and there are really deep work of Bombieri Pila and so on. And the best known, which is not sharp, is something like r to the gamma. Gamma is a fraction. I didn't want to write here because it keeps changing and improved, but it's a fraction which is not that small, okay? So this obviously was not good enough, and so for about 20 years, the problem was stuck. We could only do Strickard's estimate in this deterministic manner just for rational tori. But then in 2014 or so, Bourgain and Demeter solved not exactly Strickard's estimate per se, but solved a very important conjecture in harmonic analysis called the L2 decoupling conjecture. Now it's a theorem. And I wanted to explain a little bit what that is. So here you see a parabola, and this parabola is actually in the frequency space. Okay, so you have the variables Tx in the physical space. Take Fourier transform, you have variable tau k. And why do I draw here a parabola? Well, if you remember when we wrote the solution of the Schrödinger equation, there was a tk square. That k square accounts for this parabola here. Anyway, for the L2 decoupling, what they were proving was the following. So take a neighborhood around the parabola itself, split it into squares or rectangles. There's a special ratio between height. Oops, I don't know why this is happening. Okay, between the height and the base. But anyway, let's call theta these rectangles. Let's split f, or let's write f as a sum of f theta, where f theta is f, such that when you take Fourier transform of it, lives on this rectangle theta, okay? Now, this happens a lot in harmonic analysis. What you want to do is you want the size of f, in whatever norm you're looking at, in this case with a certain LP norm, in terms of the size of f theta. But of course, the problem here is that you might overcount it, because there'll be products that you might overcount. So you need to be very careful. And what is a way of avoiding this overcounting? Well, this is done by deep theorems, but in particular, I wanted to mention two particular tools that have been brought into harmonic analysis in recent years by Larry Guth. One is incident geometry, so basically understanding how you can cross different lines and such. And this is just a little picture here that represents that. And then another method is the polynomial method. And what you see here in red is just like the graph of certain polynomials. And there are ways of dividing the region where things happen in the Fourier space with special polynomial that give you good estimates. So this is not much of an explanation. But what I want to say is that this L2 decoupling, which is a proof which is purely in Rn and harmonic analysis, no number theory whatsoever, as a consequence, as a corollary, has proof of the Strickard's estimate in any tori, okay, rational, irrational, and everything. And they are exactly the same as the one of the square torus. Now, an interesting consequence for number theorists here is the following. So in the work of Bourgain, originally, this is, like I said, in the early 90s, estimate of the number of solutions to the Diophantine condition, that was in fact how many points are in the circle and they intersect the lattice, gave us estimate for multiplication of linear solutions. But now it's actually going the opposite direction. In fact, the tools used in the proof of the L2 decoupling, two of which I just explained before, I just mentioned, actually are giving tools in order to prove very important conjectures in analytic number theory. For example, Bourgain, Demeter, Guth proved the mean value theorem of Vinogradov, which consists in giving a sharp estimate of the solutions of a system of Diophantine conditions. So now we are going in the opposite direction. Okay, moving on. Once you have the Strickard's estimate for any tori, then you are able to do that iteration process that I mentioned before, and you're able to prove that this Cauchy problem has solutions. And in 2 dimensions, the regularity of the energy and the L2 is enough. And in particular, if you are in the defocusing case, like in this particular case, you can prove that the solution exists for all times, and you're good. Now, at this point, once we know that there is a solution, of course, we wanted to have some properties for it. We wanted to understand certain quantities. And I wanted to go back to the energy density. So for me, this eta tk, which is the magnitude of the Fourier coefficient square, is the energy density. And of course, we would love to have an equation that this energy density satisfies. That's, in fact, the kinetic wave equation. But that's too ambitious for now. I'm going to go back to that towards the end of the talk. So I'm going to do something a little bit easier. So this is the concept of forward cascade. And you see a little picture here on the side. That's, for me, is sort of a visual way of thinking about it. So you have your wave in the physical space, and you want to go from large frequency to small, large scale to small scale. In the complementary world of the Fourier space, so in the Fourier coefficients and the frequency, you want to go from low frequencies, where is my smile? Low frequency k to large frequency k. I should put here k greater or equal than 1. So I mean k large, very large. So the question is the following. If at time 0, I start with this energy profile here, so this is the energy density profile, which you can read in terms of Fourier coefficient, of course, then is it true that later on in time, it moves to large frequency? Well, that's not an easy question to ask because it's a pretty rigid quantity to track. In particular, because the conservation of the L2 norm, the area of the subgraph should be conserved. That will be the same. So it's not an easy thing to track, at least not deterministically. But Bourgain taught us that one possible way is the following. Well, if there is a motion from low frequency to high frequency, will be much more emphasized if we multiply the quantity that we want to track that grows, if you multiply that with a coefficient k to some power to s. Now, for people that know about Sobolev space, this is nothing else than the HS norm square. Okay, so this is the Sobolev norm. So the first question, how much can this quantity grow? The second question is, are there initial data for which this quantity actually grows? And believe it or not, both questions are not solved yet, but there are some estimates. For the first question, one estimate is, well, that quantity, if it grows, it cannot grow more than a polynomial, so of a certain degree. This is not at all sharp. And this has been obtained both by looking at, in the physical space, doing integration by parts and so on, but also in the frequency space. So we obtain the same result in both ways. An interesting thing, though, is that, and this is a result in 3D, if we consider irrational tori, very rational, though, and when I talk about being very rational, very far from being irrational and so on, this is my colloquial way of saying things, but of course, mathematically, that's you can define that properly using Diophantine numbers and so on. Anyway, so it has been proved that in 3D, if you are in an irrational torus, then the degree of the polynomial is smaller. And intuitively, this makes sense because in the irrational case, you have a little bit more room for the wave to spread. On the other hand, this growth that we have proved so far is way too big, and people believe, in fact, there shouldn't be more than logarithmic. But we don't know that. About question 2, are there initial data that actually grow? Well, even that case is not completely settled, this question. But one result that we know is the following. So let's fix S. So this is the quantity that HS of U, that's the quantity I'm looking at. Let's fix an S, that's not important, let's think it's large. Let's fix sigma, which is a small quantity, and let's fix K, which is instead a large quantity. Then I can construct for you an initial data U0, such that at time 0, this density, energy density is small. But if I wait long enough, that density becomes big, in fact, bigger than k. That's what we know. This is not enough to say that there is even a logarithmic growth, but that's what we know so far. Because I wanted to mention that part of this proof is actually can be deduced from a dynamical system type of idea. Briefly, how does the proof go? Well, we have an NLS equation down here. It's way too big as a system to look at. So what's done, we reduce it into a toy model, which has a finite number of degree of freedoms. And that toy model, we analyze the dynamics which happen on a sphere here. This is because the conservation of mass. There are these objects which are this invariant tori on the sphere itself. And really, this movement from low frequency to high frequency can be recast in the following way. We would like to show that there is an initial data which is close to the first torus, invariant torus, and it moves and avoids the obstacles and got to the end. And that is a typical thing that happens in dynamical system, and it's proved that way. Okay, moving forward, again, this is just a couple of computation that I did with some of my collaborators. I just want to see visually for you the difference between rational and irrational. So in this first picture, we represent the initial data that excites only the very small modes near 0, and then they evolve. And you can see this is what happens when you are in a very rational torus, square root of 2, the period, it's actually very rational in one of the two coordinates. And this is what happens when you are in the rational. It spreads up much faster. And this is a similar kind of point. What you see in the dotted line is what happens to the evolution of that quantity that I call gamma s when you are in the rational torus, and the other one down below the non-dotted line is what happens if you are in the irrational one. So why is it important to think about these questions of these differences between rational and irrational? It's because people tend to use as approximation of natural situations boxes with periodic conditions, because those are easier to control. But now we realize that really depends what these periodic conditions are, and it depends what is the phenomenon you want to study, and if there is such a difference between rational and irrational, that has to be kept into account. Okay, so one last bit that I want to mention is that another great aspect of these equations that have been introduced from the beginning is that you can think of them as infinite dimensional Hamiltonian systems. Now, the finite dimension Hamiltonian system have a great, very rich mathematics behind it. And it's, from a mathematical point of view, interesting to see whether those theorems move over in the infinite dimension case, but also studying the system as an infinite dimensional Hamiltonian system, like I'm going to say in a second, it gives answers to questions that come from physics as well. So what I want to say is that there is a beauty both mathematically and physically. So let me try to explain how you can look at this in a as an Hamiltonian system. Well, it's very simple. You take the Fourier coefficient, you divide into the real part and the imaginary part, and then you can just work that out, and you see that what happens is that this Koshi problem that it's written in the physical space can be written in this infinite dimensional Hamiltonian system in the frequency space. Why is it infinite dimensional? Because it's indexed by k, and k, I mean 2 dimension, is in Z2 in the lattice. Okay, so you probably remember, or whoever took some kind of ODE, you probably seen this picture. This is the finite dimension case. And over here, there is a picture of a typical representation of the dynamics of a finite dimensional Hamiltonian system. One important thing to remark is that obviously you can check the Hamiltonian is conserved, meaning whatever was at time 0 is the same for any time. But also, more importantly, thanks to the Liouville theorem, is that the volume the flow keeps the volume invariant. What that means is that if I measure the volume of a set A, and then I measure the volume of the evolution of the set A, those volumes are the same. There is another kind of trivial measure that you can use as well, which is the one that you make up by taking the volume again, and you multiply by e to the minus h. Now, h is invariant, so this also, the volume was already invariant, e to the minus h is invariant, so obviously this measure here is also kept invariant by the flow, and this is a Gibbs measure. Now, in finite dimension, this is totally trivial, but if you go to infinite dimension, you want to do the same thing. In fact, in infinite dimension, this is also called the statistical ensemble. You wanted to make sense of this measure here. Obviously, the volume measure doesn't make any sense because we are in infinite dimension. But maybe you're lucky, and this one, which I wrote in quotation mark because as it is, it really makes no sense, can be defined. And that, in fact, is the case. As long as, though, you do something to the Hamiltonian, you have to renormalize it. I'm not going to tell you what that is, but you have to, another way of thinking about it, you have to remove certain frequencies in the nonlinear interaction. So this can be made sense. Important probabilists did that. And where does this measure lives? And this is also part of the work of Bourgain. The measure lives in the following space. It's a space of functions that look like this. Well, this is 1 over k is, if you like, a very specific Fourier coefficient. And then what you do is basically switch randomly plus or minus 1. Or in other words, you multiply by gk, and gk omega are independent and identically distributed random variables. Of course, there is a probability space on the background that it's omega p if you want. That's where the measure lives. And also for this question, one would like to ask whether the flow keeps the measure invariant. That's the Gibbs measure. And first of all, does the flow exist? This is very, if you go back, this f omega that I define here is very rough. In fact, it's, if you want, in the Sobolev space h to minus epsilon. And so we don't even know if the flow exists. The Strickard's estimate actually do not work here. You need more regularity than that. And then after you make sense of the flow, then you ask whether you have the invariance. And Bourgain, in fact, answered yes to both questions, to the existence of the flow and the invariance of the measure. And really what did it for him in the proof of the existence of the flow is the fact that when you multiply a bunch of linear solutions, you still have this g and omega there, and you use the independence of them, and you don't lose that r to the epsilon when it was counting that I mentioned before. Now, if you change the degree of the nonlinearity, the problem becomes harder, and there is a really great work of Deng, Namod, and Yue. And what I wanted to mention is that this work is the dispersive counterpart of the regularity structure of Martin-Hare and the paracontrol distribution of the method of Gubin-Elim, Keller-Perskowski. And they use this method in the parabolic sense, in particular to study very singular equation as the KPZ, which is a very universally present equation. And I wanted to mention that the P here stands for Parisi, which is one of the 3 Nobel Prize winners this year in physics. Okay, now back to the final, to conclude the talk, back to the wave kinetic equation. So just to remind you, at the beginning, one of the first pictures I presented was the one of the gas, and the particle interaction give the kinetic equation. Now we have weak nonlinear interaction, so the lambda in front of the nonlinearity is going to tend to 0, and that will give us the wave kinetic equation, and that will be the equation for this. But it's not quite this. I mean, from a deterministic point of view, we cannot quite get the wave kinetic equation. We have to introduce some probability. So let me give you a quick history of this. So really, it's important to mention who are the people that actually start working on this problem very early on in physics. So Peirce for the paper on harmonic crystal is one of them. Then Klaus Hasselmann, by the way, he is the second physics 2021 Nobel Prize winner. And he, in fact, was one of the first people to write down the form of the kinetic wave equation. And then you see other names here. And of course, there are plenty of applications, and this was the reason why it was developed. And in fact, the Nobel Prize winner was in particular for the oceanography and climate type. Now, we wanted to do, this was some physics, we want to do some rigorous mathematics in it. And in fact, Spohn in his talk in the ICM of 2010 say that you just need to introduce some probability. You cannot do this just in a deterministic manner. And how do you introduce the probability? Well, one possible way is randomizing the initial data. Another possible way is adding noise in the equation, and that's a picture of the Brownian motion. Those are typical noise that you can add in there, or the two things together. So there are some striking results, recent results, that I want to mention because they are actually part of our group that's supported by Simon. And these results are also, in a way, the germs of them, and more than the germs, like a lot of the tools already present in the works of Erdős, Yao, and Erdős, Salmofer, Yao, and Lucarin and Spohn. And since 2018, some subgroups of our team have proved the rigorous derivation of the kinetic wave equation at different time scales. So the original papers by Buckmaster, Germain, Hani, and Chatat, and Collot, Germain, and Denganani, and Ampazoglu, and Collot, Germain, these were below the kinetic time. Now, there is a big discussion of what is the kinetic time, which I don't have certainly not the time to do it here. But you remember that lambda that was the constant in front of the nonlinearity? That goes to 0 in this type of derivations. And lambda to the -2 is the important time. So those results were strictly below that, but then Deng and Hani reached that time. That's a big thing. And then I did some work with the Bintran. It's a different equation. It's not the Schrödinger equation. It's higher dimension KdV type equation. So the dispersive relation is different. There are many differences in here, but also we reached the kinetic time for that. I wanted to conclude by just saying a couple of things. If you read these papers that rigorously derive the kinetic wave equation, there are many, many elements on it. A lot of the above that are already explained, dispersive estimates, but there is also a lot of combinatorics, a lot of study of certain objects, which I would like to call them Feynman diagrams. So you remember when I was trying to prove the existence of solution, I said an iterative method is what is used. So you use the Duhamel expression, and then you keep feeding inside the nonlinearity. In there, we only needed to understand like the interaction of 4 linear solutions. And that was enough for the existence. But in this type of a much more sophisticated results that we wanted to obtain, you really need to keep track of exactly of how this interaction, of this feeding back comes. And one method that helps you in keeping track of that are the Feynman diagrams. And then you need to study them. But these pictures comes from a paper, in fact, of Hasselmann. And that's how it looks like, the Feynman diagram in his paper. And this instead is a picture of the Feynman diagram in the paper of Lucarin and Spohn. This is from the paper of Deng and Hani. One thing to remark is that from each node that you see, for example here, there are 3 branches coming out. That reflects the fact that we are looking at the cubic nonlinearity. And the last one that I want to mention is the diagram that Bin and I used. You see here instead coming out 2 branches. Why? Because we are looking at a KdV, which instead has a bilinear nonlinearity. So once you have all these diagrams, it's a zoo diagrams, you have to analyze them, and you select them, and you learn that some of them are exactly the ones that will give you the explicit expression for the kinetic wave equation. And the other ones are going to have factors in front of lambda, such that when you take lambda go to 0, they disappear. But you need to understand how to do this sorting. So I'm going to conclude by a paragraph from Kolmogorov, which I thought really summarized well, better than I could express, the idea that you need quite a lot of different kinds of mathematics for here. So I say mathematics is vast. One person is unable to study all its branches. In the sense, the specialization is inevitable. Okay? I'm an harmonic analyst and a PDE. I know not much of both, I would say. But at the same time, mathematics is a united science. More and more links appear between its areas, sometimes in a most unexpected way, like the number theoretical piece that Bourgain brought in. None of the people working in PDE were thinking about that. Some areas serve as tools for other areas. Therefore, an isolation of mathematicians in too narrow borders should be destructive for art science. So with this, I will conclude. Thank you.